Thank you a lot. Thank you a lot for the invitation. Yeah, I'm going to talk about non-abelian analogues for ordinary differential equations and for ordinary difference equations. Before we will dive in some definitions, I would like to present some motivating examples. Well, for me, since I'm personally working on Penleve equations, I know some kind of a list of very nice examples of non-abelian Penleve equations. As far as I know, for the first time, they appeared in the paper by Balandin and Sokolov. They used a matrix analog for the Penleve test or Penleve-Kovalevskaya test. And by using this test, they derived two types of the matrix Penleve equations, of the first type and of the second type. Yep, and let me stress that later, very later, Всеволод Adler and Vladimir Sokolov classified matrix Penleve 2 equations, and it turns out that there are more than one matrix analog for the Penleve 2 equation. Yeah. What kind of properties do they have? Well, they can be obtained as a symmetry reduction, well known as a commutative case, of the integrable non-abelian or matrix analogues for partial derivation, for PTs. Yep, and such work, for instance, was done in the paper by Peter Olver and Vladimir Sokolov. They have considered matrix analog for the KdV equation. They propose that this analog has an infinite hierarchy of symmetries, similar to the commutative case. They studied symmetry reductions, similar to the commutative case of this equation. And it turns out that we can obtain by the same procedure the Penleve 1 equation and the Penleve 2 equation. Yeah. What else? What else we have in this story? I wanna mention a paper about quantum Penleve equations. By Nagoya, Grammaticus, and Ramani, and maybe some more co-authors, but I don't remember them. Yeah, they have considered some kind of quantization of Poisson brackets for the Penleve equations. Yeah, since the Penleve equations are Hamiltonian with a standard Poisson bracket, we can introduce their quantum analog. And yeah, fortunately, by using this, by using this procedure, we can obtain quantum analogs for the Penleve equations. Next story is related to matrix orthogonal polynomials. And it turns out that Penleve equations are closely connected with the Toda chain, and since the Toda chain has solutions in terms of the Hankin determinant, it means that we can introduce some kind of Z structure for the solutions for the Bentley equations. Yeah, and since the total chain has also solutions in terms of the matrix orthogonal polynomials, we can transfer this structure to the Bentley equations, and it was done in particular in the paper by Mattia Cafassa and Manuel. Yep. What else? Let me also mention a paper by Kawakami, who have derived matrix Bentley equations by considering matrix Schlesinger transformation for the Bentley-6 equation, and since the Bentley-6 equation is the master equation, we can by some kind of limiting procedure obtain independent equations of the lower type, and as a result, we obtain the whole list of the matrix analogs of the list of matrix analogs for all Bentley equations together with the Lex pair, because thanks to the Schlesinger transformation, Schlesinger system, we can easily write down the corresponding isomandromic problem. Let me also briefly mention the paper by Cafassa and Manuel. No, sorry, not this one. Paper by Bertolo, Cafassa, and Rubtsov. Because they have studied a connection between the non-abelian or matrix Bentley equations obtained in the Kawakami paper with the integrable systems of the colloidal type, and it gives us some kind of motivation to study these equations, since they are connected with some very important integrable systems. Yeah. Well, what I'm going to talk about this in this workshop. Well, the main idea that I really love is Ablovitz-Ramani-Sigur conjecture that says us that a nonlinear PDE that is solvable by inverse scattering method introduced by Sakharov and Shabbat. It can be solved if and only if every nonlinear ODE obtained by some kind of reduction has the Bentley property. So in some sense, we are searching for the solutions that can be whose general solutions. We are searching for ODEs that by whose we can solve the PDE, whose solutions, general solutions, have good properties, and this good property in the Bentley case called the Bentley property. Yeah. Well, roughly speaking, it means that we can prolongate our solution on the whole domain. In the case of the ODE, we are considering the complex plane. In the case of the second Bentley equations. And so my talk will be divided into 4 parts. The first part is about motivating examples. We're gonna look at matrix KdV equation and discuss its integrability and symmetries. Then we obtain a matrix first Pinlevy equation as a reduction of the matrix PDV. And after that, we will look at the discrete analogs for the first Pinlevy equation, for the matrix first Pinlevy equation obtained in the paper by Adler. So the second part is about non-commutative ODEs. We need to set up we need to set up non-abelian case, and we need to give main definitions in order to understand what exactly we want to get. And in order to study non-commutative ODEs, I will present two tools. The first one is first integrals for the ODEs, and the second one is Lex pairs. And the first integrals, and this part is based on the paper by Mikhailov and Sokolov, where they have studied non-abelian ODEs on a free associative algebra. The third part is about non-commutative analogs for difference equations, and we will go in the same way, but at the end, we will discuss a little continuous limits for these equations. It's a very natural story. When we have difference equation, we want to study its continuous limits in order to obtain differential equation. Yeah? And the last part is about methods for the derivation of non-abelian ODEs or non-abelian difference equations, and we will give some more examples. So this is the plan, and let me start with the motivating examples. So we wanna study this matrix KdV equation. Here we have matrix valued function W that depends on the variables x and t, and we do not fix the size of the matrix. In contrast to the, unlike the commutative case, we have here two terms that under the commutative reduction becomes, that under the commutative reduction gives us a well-known term in the KdV equation. And this equation was derived by analog of the inverse scattering methods. In this sense, it's integrable. And later it was studied more detailed, and it was introduced a hierarchy of commutant symmetries for this KdV equation. Moreover, one can present the Lex pair or the Lex pair of the Zakharov-Shabbat type. So it means that we have a linear system with the arbitrary vector function psi. This vector function psi depends on two variables x and t, and this function is two value. Is a two column. And in the right hand side of this system, we have two matrices, U and V. They are 2 by 2 matrices, also depending on the variables x and t, but in addition to these variables, we have one more, mu, and this parameter is called the scalar spectral parameter. Yeah? And the precise form of this Lex pair of the Zakharov-Shabbat type is given by equation 2. Yeah. 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 Let me mention that that mu is scalar. It means that when we write, for instance, this guy, it means that we have a block matrix, a diagonal block matrix with value 1/2 of mu on the diagonals. Yeah. And I hope that, but yeah, later I will omit. I will identify the unit of the algebra, yeah, because in this case we have matrix algebra, and later we will identify the unit of the algebra with the unit of the field in order to not in order to make our formulas more readable, I hope. And yeah, this system, this linear system is compatible if and only if this condition holds. It's called the zero curvature condition, and if we substitute into this equation matrices U and V, we immediately obtain our matrix KdV equation, this one. Moreover, we can study symmetries of this equation. In particular, it does not change if we have shifts along the x direction, yeah? Or if we have shifts along the t direction, or if we consider, or we can consider Galilean transformation or self-similar transformation. Yeah. So now we want to use these symmetries for the matrix KdV equation in order to obtain by reduction, in order to obtain its solutions in terms of ordinary matrix ordinary differential equation. Yeah. And yeah, here we have a result of our reduction, but let me do it step by step. So we have our KdV, matrix KdV. We consider the same symmetry reduction that leads to, as in the commutative case, it leads to the Penlevy-1 equation. So it's a combination of the Galilean transformation and the shift along the t direction. So we introduce new variables, y, that depends on z, and z is a function in x and t. If we substitute these two guys into the matrix KdV equation, we will obtain the third order ordinary differential equation that can be integrated one time. And after the integration, we obtain the second order differential equation, but it contains one arbitrary term. Oh, sorry, but it contains one arbitrary term A, this arbitrary matrix, constant matrix. And if we make a commutative reduction for this equation, we can absorb this additional constant A by the shift of the variable z. Yeah? And here we have the difference between the matrix Penlevy-1 equation, matrix ordinary differential equation, and commutative differential equation. Yeah? Non-commutative differential equation equations might contain non-abelian arbitrary parameters that cannot be reduced by some transformations in the equation. It's very nice property. Next step is to extend this reduction in order to obtain Lex pair, isomandromic Lex pair for the Penleve equation, in order to justify its integrability. What we do, the following change for the spectral parameter. And after this change, supplemented with the previous one, the zero curvature representation becomes to the form 4, given by equation 4. Here we have two new matrices, A and B. They depend on variable z and on the spectral parameter, on the new spectral parameter lambda, and can be expressed in terms of the matrices U and V as follows. Yes, it's given by equations 5 and 6. And if we substitute these two matrices into the zero curvature representation, we obtain our matrix first Penleve equation that contains arbitrary matrix constant. Well, yeah, so it's a very nice idea to reduce to find some integrable PDEs, reduce them by symmetry reduction to the ordinary case, and try to obtain some ordinary differential equations together with their Lex pair. And because if we have a Lex pair on the level of the integrable PDE, we want to transfer this integrability property in the sense of the Lex pair to the ordinary differential equation. And now let us look at this Penleve 1 equation, matrix analog for the Penleve 1 equation. What do we know about it? So as we have already discussed, the matrix Penleve equation solves the matrix KdV equation. Thanks to the reduction, P1 admits a Lex pair that is called in the ordinary cases isomandromic representation. As I mentioned in the beginning, P1 passes as a matrix analog for the Penleve-Kovalevskaya test, and it was introduced by Balandin and Sokolov. And moreover, we can study Hamiltonian structure for this Penleve 1 equation. Here we have a function h, and dependent on two variables, dependent variables u and v, and the dependent variable z. Well, it's non-autonomous Hamiltonian because we have that explicitly here. If we consider this constant Poisson bracket between the matrices U and V, we can obtain these motion equations for the matrix variables U and V. It's easy to see that we can reduce this system of the this second order system of the first order ODEs to the Penleve 1 equation just by yeah, just by substituting this variable v into the second equation. So this equation has many nice properties. What I wanna add else is the following. If we look at this equation more precisely, we can see that we actually don't use the specific of the matrix algebra. Yeah? And um, and um, and it means that we can generalize this case. We wanna generalize this case to the arbitrary algebra, arbitrary associative unital algebra, equipped with the derivation. Yeah? So this algebra should satisfy the Leibniz rule. It's a crucial property of this map. And yeah, I will give later more detailed description of this case, but we are at this moment we're looking at this briefly. Yeah. And we suppose the following rules for this derivation. Yeah, that a is a constant. If we take the derivative of that, we obtain a unit of our algebra, of course. But as I said, we identify the unit of the algebra with the unit of the field. And so in the notation of for this algebra A, we have some indexes some indexes I is greater or equal to 0. We will use it in order to make this map from A to A and to introduce this some kind of analog for the derivatives. Yeah? When we act by this derivation on the variable u sub I, we obtain u sub I plus 1, and we will denote it by the I plus 1 derivative of u, and similar for v. Yeah. Well, and the last part of this slide is related to the so-called fully non-abelian case that I hope Volodya Rubtsov will discuss later. So in general, we can't absorb this matrix A by the shift of the variable z. But suppose that we can. Then we can introduce the new variable bar z, and after this change, we introduce some kind of new non-abelian new element of our algebra A. So it means that Z is now a non-abelian element, so it doesn't commute with other elements of our algebra. Yeah. And it turns out that after this change, we can easily rewrite the Pinlever-1 equation and its Lex pair, and and its Lex pair, and this Lex pair will be the zero curvature condition is still equivalent to this Pinlever-1 equation with non-abelian independent variable. Yeah? So this is another story, but I just wanted to mention that we can do it in some cases, and we have some more examples for the Pinlever-2 equation and for the Pinlever-4 equation. Well, yeah. next part is about discrete analogues for the Pinlever-1 equation, for the matrix Pinlever-1 equation that we have already discussed. Well, starting from the matrix Volterra lattices, labeled by VL1 and VL2. Here we have one matrix variable, U, that depends on the variable X. And we have, and we consider this matrix variables on the lattice. Yeah. Several Tandler have obtained these two lattices. Yeah, they are different because in the second equation we have the transposition. Yeah, these two lattices were derived by the by the symmetry method, and both of them has both of them have also discrete Zakharov-Shabat type Lex pairs, but I will discuss it a little bit later. Yeah, and well, by considering reductions of these two lattices, we can obtain these two discrete analogues for the Pinlever-1 equation. Yeah. So so if you're not familiar with the Pinlever equation, it's actually it doesn't matter because we are just looking at the examples of non-abelian discrete and differential equations. Yeah, and yeah, and these two discrete analogues are now have variable u that is also matrix, but it doesn't depend on the variable x. X now is a parameter of this equation. Yeah? So in this sense, we have ordinary discrete equation. Yeah? And but these two equations are non-autonomous because we have a constant parameter gamma that depends on the lattice. Yeah. So this is another example when we started from the integrable discrete matrix PD, can consider its symmetry reductions, and the symmetry reductions lead to ordinary difference equations that are also have some kind of integrability. And moving to this part, I want to say that these two lattices can be presented as a linear system for the vector function psi, arbitrary vector function psi. This vector function depends on the lattice, yeah, and on the variable x. And in the right-hand side of this system, we have two matrices, L and M. Yeah. They are 2 by 2 matrices depending on the spectral parameter lambda. Yeah. And it turns out that the reduction for the equations can be extended to the reduction for the Lex pairs. Yeah. And after that, we obtain system 10, yeah, for the matrix function f, matrix valued function f of the size 2. Yeah? This matrix valued function depends, still depends on the lattice. Yeah, and instead of the parameter x, since x is a parameter for the discrete Penlever equations, we obtain the dependence on the spectral parameter of the function phi. I'm sorry, it should be lambda here also. Yeah. Yeah, and by this reduction, we obtain new matrices A and B, and for instance, that are also that also depend on the spectral parameter lambda. And for instance, for the first discrete analog for the Penlever 1 equation, these matrices are given by formula 11. Yeah. So we can write down the compatibility condition for this system. And if we substitute these matrices A and B into this compatibility condition, we obtain the discrete analog for the Penlever 1 equation. Okay. So let us make some observations related to the considered examples. Yeah, our examples under the commutative reduction. So in the case of the matrix, or in case of the matrix of the size 1, coincide with the well-known scalar analogs. All considered examples are the reductions of integrable matrix PDEs or matrix or difference matrix PDEs. Yeah. And this reduction can be extended not only on the level of the equations, but also on the level of the Lex pairs. Yeah, and thanks to this fact, we can justify an integrability for the reduced matrix ordinary differential equations or ordinary difference equations by presenting their Lex pairs. Yeah. And one more observation is the following. So in the non-abelian case, these equations can contain arbitrary matrix constants. Or, as I said, can be generalized to the fully non-commutative case that I will not discuss in detail in this series of talks. Yeah, and the last part, the last part is about further generalization of these examples. Yeah, instead of the matrix algebra, we can, since we don't use this matrix setting at all, we can we wanna generalize these equations to the case of an arbitrary associative unital algebra with a derivation or without it, if it depends on the case of the differential equation or difference equations. And as we remember, the second discrete analog for the Penlever 1 equation has matrix transposition. in the expression, and it means that we need to introduce some kind of an involution of A on A that is just some kind of analog for the matrix transposition, but in the case of the arbitrary associative algebra A. Yeah, and the last thing about this stuff is it's related to the continuous limits. So we know that the commutative case, starting from the difference equation, we can study its continuous limits. So it means that we make the size of the lattice very small, and due to this we introduce this change for the variables. In the right hand side we have the lattice parameter m and the parameter epsilon, the small scalar or commutative parameter. And we supplement this map by the following changes. So we send the function on the lattice to the just function u, that doesn't depend on the lattice. And each function on the lattice shifted by k, by the integer number k, we send to this expression. This this is an analog of the Taylor expression of the Taylor series in the commutative case. And then we substitute all this stuff into our difference equation, and these changes must be chosen in such a way that we can take the limit, this limit. And after this limit, we can obtain ordinary differential, non-abelian ordinary differential equation starting from the difference equation. I think that we finished the first part. Do you have any questions, remarks, or can we go further? No questions? No. Okay, let us move to the second part. And now we are going to discuss non-abelian ordinary differential equations. Let me take some kind of setting for this case. So we wanna introduce J sub I, where I is equal to 0, 1, 2, and etc. They are free groups generated by the finite set of the variables x, of the elements x, x1 sub I, x2 sub I, and etc. until xn sub I. And for the and we set this notation for the y for the 0y. Then we consider a unital associative algebra, a group algebra over the field C. In fact, we can use any other field, but we fix its we fix that its char is equal to 0. And our algebra A is given by the direct sum of these groups J sub I. Yeah. Well, yeah, we wanna use involution on this algebra. Let us call it tau. And we define for this action of tau on the elements of A as follows. For any generator of our algebra A, tau acts trivially, but if we have any other elements from our algebra A, tau acts on these elements by this rule. And we will call this involution a transposition. And in order to work with matrices over our algebra A, we extended this action as follows. We have some matrix M over our algebra A, and tau acts on matrix entries by this formula 17. We permute, we make a transposition in our matrix for, we make a transposition of our matrix M, and in addition, we make a transposition for our elements from the algebra A. And for simplicity, we consider an element Z as a central element of our algebra A, and also for the simplicity, we consider all parameters that we label in by Greek letters as a scalar parameters, as parameters from our field C. And the first remark is just about the fact that we can include this element Z and all constant parameters alpha sub I to our algebra A, but we don't care about it now. In particular, when we have only three variables, x1, x2, and x3, and if we consider an element of our algebra P that is given by this monomial, then if we act if we act on it by tau, we obtain the following result. We just permute. Elements in this monomial by the rule 16. Well, in fact, this involution is not the same as the transposition, but it still is still useful when we are working on classification of ordinary differential equations or ordinary difference equations, because we have a group that acts on the list of these equations. Next part is related to the derivation of our algebra A. Remark about the identifying the unit of A with the unit of the field. Anyway, we call a C-linear map from A to A that we denote by the D sub Z that satisfies the following properties. For any constant, we have D sub Z over alpha sub A is equal to 0. If we take a derivation of our central element Z, we obtain the unit of our algebra A. or just one. Yeah, and we shift our variables x sub ki by the union. Yeah. And very important property is the property 20. Yeah, it's just the Leibniz rule. It's very important that for any two elements from our algebra A, we acting by d over z on this element, on these two elements, but we strongly follow the order in this in this derivation. Yeah, and this map is called a derivation of our algebra A, and for the simplicity, again, we denote for the generators that d sub z over xk is just x prime, and so on. Yep. Not very so trivial, but useful remark that the involution tau and derivation of A commute with each other. It's important to remember about. Um, the first example of this of a blind of this definition is some kind of very trivial, but yeah, let us look at it. So if we consider the case of two variables and consider the same element of our algebra A, and we want to take the derivative, we want to take a derivation of this element. Yeah, and the computations are pretty simple, so we just use the Leibniz rule, yeah, and put and take a derivation of each element or in this monomial, yeah, and as a result we obtain this expression. Yeah, it's very natural and not very complicated. Yeah. But one more useful example, is the following. Let us consider the case when n is equal to 1. So we have only one x. 1x in our algebra A, and we wanna compute the derivation of x1 of the inverse of x1. Yeah, since because let me recall that we are working with not only algebra but the group algebra. Yeah, and by the definition of the inverse element, it satisfies this property. So then by using this property and by using the Leibniz rule, we can compute expression 22 just by taking the derivation of the left-hand side and the right-hand side of this expression, of this one. And since it's an identity, we can easily obtain the answer for the derivation of the inverse of x1. Yeah. And these computations are just repeating the same arguments when we taking a derivation of the matrix value function, yeah, and the answer is the same, yeah. Okay. Probably I think that it would be nice to okay. So I have only 6 minutes, but yeah. Main definition. We will call a system of non-abelian ordinary differential equation as the following set of relations, yeah, that are given by the formula 24. In the right-hand side, we have the first derivation of the variable of the generators xk. Here, I is equal to 0 when we're taking when we're taking the derivation of xk. We assume that I is equal to 0. And the right-hand side is just some element from our algebra A. Yeah. And for again for the simplicity, we consider some kind of the first order analogs for the first order differential equations, but it can be generalized to the high order. And this set of relations we call a system of non-abelian ODEs. And if for some k the right-hand side depends explicitly on the variable z. This system is non-autonomous, and otherwise it's autonomous. As I said, we gave a definition of a system of first order ODEs, but it's easy to introduce a non-abelian analog for a system of high order ODEs. And the second remark is about the PDEs. So if we can introduce a set of derivations, d sub z1, d sub z2, label it by d sub z1, d sub z2, and so on. And then system 24 can be generalized to the case of non-abelian PDEs just by considering different d sub zl in the set of in the set 24. And let me present an example. When n is equal to 1, in this formula 24, let us consider two systems. The first one is just x1 prime is equal to x1, and the second one is x1 prime is equal to zx1. Recall that that is the central element, and it doesn't matter. And we don't care about the position of z in the right hand side of this expression. And according to this definition, the first equation is non-abelian analog for the autonomous ordinary differential equation, and the second one is an example of non-abelian analog for the non-autonomous differential equation. And both these systems, remembering the property of commutativity between the involution and the derivation of our algebra A, these two equations are invariant under the tau function. For instance, for the second one, computations are pretty simple. So we just take the we just act by tau on the right hand side, and as a result we obtain x1 prime, because the derivation and the tau action commute with each other, and the tau acts on the generators trivially. But for the right hand side, if we act by tau on the right hand side of this equation, this non-autonomous equation, we just apply the rule that we need to permute elements in this monomial, and as a result we obtain this stuff. Then we recall that for the generator, this involution acts trivially, and of course it acts trivially for any central element of our algebra A, and therefore we obtain this expression. But since x1 and z commute with each other, yeah, we just obtain the initial expression for our equation, non-autonomous equation. Yeah. Well, actually, I think that it's a good point to stop if we, yeah.
No problem. This is flexible, so you can extend. Yeah, please continue.
Yeah, but how many time do I have?
Now it's just 60 minutes, but no problem to extend.
So as you wish, yeah, I can continue, yeah, in order to finish this part. But I hope but I think that it's about maybe 20 minutes. Yeah.
20 minutes.
Yeah, maybe it's too much, and it's better to
Yeah, I
continue.
think it's okay.
Okay, as
Yeah.
you wish.
Yeah.
Yeah. Yeah. So maybe I want to briefly describe these properties. So yeah, we give the main definition for our system of ordinary differential equations. Yeah. In the non-abelian case, and now we wanna study them. And the first tool that I'm gonna present is first integral. Is first integrals. So again, we have this system, and we call an element I from our algebra a first integral for the system 24. If d z over I, is equal to 0. And it's very natural, because we have the same definition, in the commutative case. And when we have two variables, if we consider the case of when n is equal to 2, and let us look at the element I that is given by this commutator of two elements x1 and x2. And one can verify that this element is the first integral in the sense of definition form for the system 28. So the verification is just a direct computation. We take a derivation of our element I. We just using the Leibniz rule. Then each x prime we replace with the corresponding expression in the right hand side of the system 28. And then we obtain this huge, but sorry, this some mistake. I need to correct it, but later. Yes, and after some corrections, we obtain that this expression is just equal to 0. Sorry, it's simple. Here I forgot to put x2. Now it's clear that this expression is equal to 0. But if we consider another system, system 13, and if we verify, if we take a derivation of this element I, and verify is it a first integral for this system or not, what we have here. We again take the derivation by using the Leibniz rule. Obtain this expression. Then we replace each x prime by the right hand side by using the right hand side of the system 13. Obtain this huge expression. And we can see that that it's not equal to 0. So even for the what I wanna mention here, in the non-abelian case, we have a big difference between the systems. For some of them can have some of them can have some first integrals, but another one cannot have them. And however, under the commutative reduction, this first integral is nothing but 0. But we have one more observation, and this observation is the following. So this expression not equal to 0 in this direct way, but it's equal to 0 up to the commutator of these two elements x1 and x2. And it's under this condition, this element is just 0. And this observation this observation is useful and motivating to introduce another type of first integrals. And let me give you a definition. So we say that two elements, if two elements P and Q from our algebra A, to be more precise, their difference belongs to the commutator of our algebra A with itself, then we write that P is equivalent to Q. And in this case, in this sense, these two expressions are the same. In these two expressions in example 5 are the same. And a class of P, of the element P from our algebra A in the space, it's no longer the algebra, the space in the linear space. We denote this class of P by trace of P. And so now we are ready to give a definition of another type of first integral. An element E from our algebra A is the first trace integral, because we have this notation in the definition 6. For the system 24, if dz over trace of I is equal to 0. And then the previous example becomes trivial, because our element I is a trivial trace integral for both systems, because I is equivalent to 0 in the sense of the definition 6. I have here a remark, but let me skip it. No. I think that I need to mention it. Well, why this second definition of the trace of the first integrals is important? Because it's very useful if we want to introduce a non-abelian Hamiltonian formalism for the non-abelian ordinary differential equations. I will not discuss it in these talks, but if you want to look at it in more details, I recommend to look at the paper by Maxim Kontsevich, where this non-abelian Hamiltonian formalism was introduced for the first time, and also two very nice papers by Peter Olver and Vladimir Sokolov, and by Alexander Mikhailov and Vladimir Sokolov also. Well, the last thing related to the second part of this talk is the following. Now we want to introduce Lex pairs in the non-abelian case for the ordinary differential equations. So in addition to the derivation d over z, we will consider a derivation d over lambda, where lambda is also a central element of our algebra A. But we have different properties for this derivation. Of course, it should satisfy the Leibniz rule, but it has different action on the elements of our algebra A. If we take d over lambda, or if we act by d over lambda, d sub lambda over lambda, we obtain a unit of our algebra A. And in other cases, we just get zeros. And this derivation is just analog in the non-abelian case for the spectral parameter. We will call lambda is spectral parameter. So we have two types of systems: non-autonomous systems and autonomous systems. And for these two different types, we have different types of Lex pairs. If system 24 is non-autonomous, and it's equivalent, then we consider this condition 34. That is called the isomodromic representation or zero curvature condition with some matrices A and B. And these matrices they might be of different size, but they must depend on the parameter on this parameter lambda and on the parameter z. And if our system 24 is equivalent to the zero curvature condition 34, then these two matrices A and B are called isomodromic Lex pair and an isomodromic representation for the system 24. And we have already seen this example for this case, when we were discussing the matrix first Penlever equation. Well, but if system 24 is autonomous, we have another type of Lex pairs, or just I would say we just have a non-abelian analog for the Lex equation. Well, again, we have two matrices of size n, L and M. Sorry, here's no, that's okay. These two matrices can depend on the some spectral parameter lambda, but it's not necessary. It's not necessary. And if autonomous system 24 is equivalent to this equation 35, that we will call a non-abelian Lex equation, then these two matrices L and M are called the spectral Lex pair for our system 24. So two different types of systems, two different types of Lex pairs for the systems, in order to justify their integrability. And let me stress that existence of Lex pairs is invariant under the Tau action, but we need to change our matrices A our Lex pairs, yeah. And in addition to transposition, yeah, of the matrices according to the tau action, yeah, we need to change the sign in the isomandromic Lex pair, yeah, and the sign of matrix M in the isospectral Lex pair, yeah. Well, yeah, and next one is next slide is about some examples. Yeah, I think that, yeah. Let me open the whole slide. Yeah, let us return to the case of the system that have both first integrals, trace integrals, and just first integral. Yeah. Again, we set n to 2. And consider system 37. This system is autonomous, and we want to present its a spectral Lex pair, and it turns out that we can. We have matrix L and matrices L and M. There are 2x2 matrices. Yeah. Matrix L depends on the spectral parameter lambda. Matrix M doesn't depend. Yeah. And if we substitute these two matrices into the Lex equation, we can see that this Lex equation is equivalent to our system 37. Yeah. One more thing. One more thing about the connection between non-autonomous systems and autonomous systems is the following. Well, starting from the non-autonomous system, we can introduce its autonomous analog, by the following way. So we just introduce new central element of our algebra A, T, and replace in the non-autonomous system in the right-hand side all elements Z by T. Yeah. And we assume that dz over T is equal to 1. And then our non-autonomous system becomes the autonomous one. Yeah? And this procedure we call an autonomization. And it turns out that we can do the same stuff in order to obtain from the isomonadromic Lex pair, it's is a spectral Lex pair. Yeah. So, and we have the following proposition that I give without proof, but the proof is pretty simple. That if we have a non-autonomous system that has isomandromic Lex pair, then the corresponding autonomous system obtained by using the procedure of autonomization, we obtain an autonomous system with the corresponding isospectral Lex pair. And let me present an example, simple example that illustrates this proposition. We have the first Penlever system without arbitrary constant A. Let's forget about it. It's the first Penlever equation can be written as a system of as a second order system, and we can introduce its autonomous analog by using the definition 10, just by replacing this element Z in the right hand side by T. It should be T. And then the system becomes an autonomous system, and we can do the same for the Lex pair, And the corresponding ether spectral Lex pair for the autonomous system is given by these matrices L and M in the formula 13, sorry. And here we have this autonomous, this parameter T that was replaced, this autonomous parameter T, sorry. Yes, and the remark why I love this example is that the first Pendeler equation is non-autonomous. So in the abelian case or in the scalar case, the first Pendeler equation is an autonomous analog for the ordinary differential equations that can be whose solutions are given by the Weierstrass P function. And well, it turns out that we can somehow introduce non-abelian analog for the Weierstrass P function, by using this procedure of autonomization of the first Pendeler equation, And sorry for the for this delay. I think that it's a good point to stop because next part is about non-abelian difference equations.
Okay, so thank you very much for the very clear introduction.
Thank you for your attention. Thank you so